Okay, this is lesson 80, and we are going to talk about three more trig identities that you will need to know. A says sine squared theta plus cosine squared theta equals 1. That is very important. It is something you will have to have memorized. It's not hard to prove. If you have a triangle, right triangle with sides A, B, and C, and angle theta, you know already from the Pythagorean theorem that a squared plus b squared equals c squared. You know by the definition of your trig functions that sine theta is a over c, cosine theta is b over c, and tangent theta is a over b. So you can prove that sine squared theta plus cosine squared theta equals 1. Sine theta is a over c, so when you square it, you get a squared over c squared. And cosine theta is b over c, so when you square it, you get b squared over c squared. If you add those two fractions, you get a squared plus b squared over c squared, and we know that a squared plus b squared equals c squared by the Pythagorean theorem, and so we get 1. Sine squared theta plus cosine squared theta equals 1. Very important. B, 1 plus cotangent squared theta equals cosecant squared theta. I'm not going to prove it, but you can prove it in exactly the same way. Tangent squared theta plus 1 equals secant squared theta. Can prove that exactly the same way using this triangle. These are three trig identities that you do need to memorize. If you have the first one memorized, you can get the other two. So let's just look at how we can make sure we know what they look like in all their forms so that if we're doing a trig derivation, we will recognize them. So sine squared theta plus cosine squared theta equals 1. You can rewrite it as sine squared theta equals 1 minus cosine squared theta. That's one way you might see it. Another way is cosine squared theta equals 1 minus sine squared theta. 1 plus cotangent squared theta equals cosecant squared theta can be written as cosecant squared theta minus cotangent squared theta equals 1. Another way to write that is cotangent squared theta equals cosecant squared theta minus 1. Tangent squared theta plus 1 equals secant squared theta can be written as tangent squared theta equals secant squared theta minus 1, and secant squared theta minus tangent squared theta equals 1. Now this looks like a lot to memorize, and it is. I don't have all this memorized. I just go with sine squared theta plus cosine squared theta equals 1, and I use that to find everything else I need. So if you were to take A, sine squared theta plus cosine squared theta equals 1, and you were to divide it by sine squared theta, you would get 1 plus cotangent squared theta equals cosecant squared theta. So I just got the second identity by dividing the first identity by sine squared theta. So why would I memorize 1 plus cotangent squared theta equals cosecant squared theta when I don't need to? You can do the same thing to get from A to C. You can divide sine squared theta plus cosine squared theta equals 1 by cosine squared theta. If you do that, you will get the third identity, tangent squared theta plus 1 equals secant squared theta. So it's not really necessary to memorize B and C. All right, so you'll use these things in a problem like this where they want you to show that secant squared x minus tangent squared x over 1 plus cotangent squared x equals sine squared x. Now, if I had memorized that 1 plus cotangent squared x is equal to cosecant squared x, I could plug that in, but I haven't memorized it personally. So when I see something like this where the left side of the equation has all these different functions in it, and I see that I have a sine function all by itself on the right side, what I'm going to do is start with the left side, and I'm just going to change all of that to sines and cosines. I'm going to rewrite it all as sines and cosines. So secant squared x is 1 over cosine squared x, so I'll just go ahead and write that. That's just the definition of secant. Tangent, I know, is sine over cosine, so tangent squared x is sine squared x over cosine squared x. And on the bottom, I've got 1 plus cotangent squared, which is cosine over sine. So that's all I had to do. I didn't even use any of those identities yet that we learned in the previous slide. So now I'm going, on the top I have a common denominator already, so I can just add those two fractions and get 1 minus sine squared x over cosine squared x. And then in the denominator, I can get a common denominator of sine squared x by multiplying 1 by sine squared over sine squared. If I look at the numerator of this complex fraction, I've got 1 minus sine squared x over cosine squared x. I know that since sine squared x plus cosine squared x is 1, that means that 1 minus sine squared x is cosine squared x. So I can substitute that. Then in the denominator of this complex fraction, I can see that I have sine squared x plus cosine squared x over sine squared x. I know that sine squared x plus cosine squared x is 1, so I can rewrite that denominator as 1 over sine squared x. Therefore, I have 1 over sine squared x, which is equal to sine squared x, and that is what I was looking for. Okay, so now I have 1 over tangent A plus tangent A equals secant A times cosecant A. This time, most of the time for these kinds of trig derivations, I will start with the left side and try to make it look like the right side. For this one, I'm going to work with both sides at the same time and try to make them look like each other. So I'm going to go ahead and replace all of these things here with sines and cosines again, because that's what I'm most familiar with, and so why not? All right, so for tangent, I know it's sine over cosine, so I'm going to go ahead and replace the tangents with sine over cosine. And then on the right side, I'll go ahead and replace secant and cosecant with 1 over sine and 1 over cosine, because that's what they are. So that is equal to cosine A over sine A. And sine over cosine A is still sine over cosine A. And the right side, I just multiplied those two fractions together. All right, now I can get a common denominator on the left side by multiplying the first fraction by cosine A over cosine A. And then I can multiply the second fraction by sine A over sine A. So I'll get a common denominator. So now on the left side of this equation, the common denominator is cosine A sine A. I'll just rewrite the right side of the equation. Now on the left side, I can go ahead and write this all as one fraction, cosine squared A plus sine squared A, all over cosine A sine A. And the right side, I'm not doing anything to it. It's just the way it is. And now I can see that these two things equal because cosine squared A plus sine squared A is 1. So that is the same thing as the right side. All right, for this one, I am going to rewrite the left side with a common denominator. So I want, on the left side, I want to have a common denominator of 1 plus cosine A, 1 minus cosine A. So to do that, I'm going to have to multiply that first fraction by 1 minus cosine A over 1 minus cosine A. And the second fraction, I'll have to multiply top and bottom by 1 plus cosine A. So I'm just getting a common denominator on the left side of this thing. Okay, now that I have a common denominator, I can add these two fractions together. The cosine A's, I've got a negative one and I've got a positive one, so they're going to cancel. So I will just have 2 over 1 minus cosine A times 1 plus cosine A. And I can see that the denominator is a difference of squares. So I can rewrite it as 2 over 1 minus cosine squared A. And I know that since cosine squared A plus sine squared A is 1, 1 minus cosine squared A is sine squared A. And since cosecant squared is 1 over sine squared, this is equal to 2 cosecant squared A, which is what I was trying to get. So I find that often I will just be replacing things with sines and cosines or getting common denominators, that kind of thing. These are the kinds of skills you put to use in these trig identity problems. Even though it seems like you have to know lots of trig identities to do these problems, you really don't. You just have to know the definitions of the trig functions, and you do have to know that cosine squared theta plus sine squared theta equals 1. Yeah. All right, moving on. Here's another one. All right, so again, this looks like a situation where I want to get a common denominator. So I'm going to multiply that first fraction by cosine A over cosine A. I'm going to multiply the second fraction by 1 plus sine A over 1 plus sine A because I need that in my denominator. All right, so now I can add those two fractions together, and I will get cosine squared A plus 1 plus sine A quantity squared over 1 plus sine A times cosine A. Next, I am going to go ahead and multiply out 1 plus sine A quantity squared. So I've got my cosine squared A. Now I'm multiplying out that second term up there and leaving the denominator the way it is. And now I can see, if I rearrange that numerator, I have on top, you can see that I have a sine squared A plus cosine squared A, and I know that that equals 1. So I'm going to go ahead and add that together and get 1 for that. So that's all I'm doing in this next step is just rewriting it. So I rewrote that denominator as 1 plus 1, which is 2, plus 2 sine A. Now, if I notice, I can factor out that 2 in the numerator. 2 times 1 plus sine A over 1 plus sine A cosine A, and now I have a factor of 1 plus sine A on the top and the bottom. They can be canceled, and I end up with 2 over cosine A, and since cosine A is the reciprocal of secant, this equals 2 secant A, which is what I was trying to get. This is lesson 81, the law of cosines. To solve any triangle, we have to know one side and two other parts. We talked about this before. If you're going to solve a triangle, you have to know one side and two other parts. To use the law of sines that we learned in lesson 72, we have to know an angle and the side opposite to that angle. But if we don't have a side and its opposite angle, we must use the law of cosines. We can write the law of cosines in 3 ways, but we don't really have to. It all means the same thing. A squared equals b squared plus c squared minus 2bc cosine A. Now, this looks hard to memorize, but it's really not. The A right here these are A, B, and C are all sides. Okay, these are all sides of the triangle. There's only one angle in this whole equation, and that is right here. That angle is the angle opposite A. A is on the left side of the equation, A squared. The angle opposite to A goes here inside this cosine, and all the other things in this equation are the other two sides. You've got one of the other sides squared here, you've got one of the other sides squared here, you're adding them, and then you are subtracting 2 times the product of the other two sides times cosine A. And these are just, if you use a different side, it's all the same thing. All right, you want to solve this triangle for its unknown parts. We have 2 sides and 1 angle. We don't have the side opposite that angle, so we can't use the law of sines. We want to use that angle in our law of cosines. So if we're going to use that angle 36, we need to use the sign opposite to be on the left side of the equation. So x squared will be on the left side of our equation. And that cosine that's at the end of the equation will have that angle, cosine 36. The rest of the equation is just the other two sides in different formations. So 7 squared plus 10 squared minus 2 times 7 times 10. All right, now I can just multiply all that out, and I will get 149 minus 140 cosine 36. If I punch that into my calculator, I will take the square root of it, and I will get about 5.98. So I have my x, and now since I know an angle and its opposite side, I can use the law of sines to finish this. So sine 36 over 5.98, which I just found, is equal to sine y over 10. If you cross multiply, 10 sine 36 over 5.98 is going to be sine y. So if you punch that into your calculator, 10 times sine 36 over 5.98, take the inverse sine to figure out what y is, and you will get that y is about 79.39. Now remember that 79.39 is not the only angle that has that sign. So this other one does too. That's 180 minus 79.39, which is 100.61. So that is another possibility for y, and we can't completely say that it is not a possibility. So remember, whenever you're using inverse sine to figure out an angle, you have to take into account that it could be the acute angle or it could be the obtuse angle. Now in this triangle, it is not completely clear that y is acute or obtuse. It looks a little bit obtuse, but when it's this close, you can't assume. All right, so we're going to go ahead and see what m is and see if that helps us figure out which one of these y should be. All right, so we'll use the law of sines again. Sine 36 over 5.98 is sine m over 7. If we cross multiply and take the inverse sine, we get that m could be 43.48 degrees, or again, we have to look at the other possibility that it could be 180 minus that, which is 136.52. And really, if you look at the picture, you can absolutely tell that m is acute. There's no question about it. So really, if you take 36 and add 43.48, it's clear that y has to be 100.6 to make the triangle add up to 180. So that would be the value of y that we would choose. So the three angles have to go together. They have to work. You can't just ignore the possibility that one of the angles in the triangle is obtuse. It could be. So always when you're using inverse sine to find an angle, or inverse cosine for that matter, you have to check the two possibilities. Okay, so now we have one where none of the angles are there, so we don't have any angles. And so what we're going to do is we can just pick any side to put on the left of the equation. So if I choose 7 to put on the left side of my law of cosines equation, that would be 7 squared. And that means that the angle I put into the cosine has to be the angle that's opposite 7. So that's x. Now I just fill in the other sides where they go in the law of cosines. 5 squared plus 8 squared minus 2 times 5 times 8. Now I will multiply all that out, and I'll have 49 equals 25 plus 64 minus 80 cosine x. If I add 25 and 64 to get 89 and subtract that on the left, I will have negative 80 cosine x, and then I will divide both sides by negative 80, and I get that 1/2 is equal to cosine x, and that happens when x is 60 and when x is 300. Now there's no way x can be 300 because there's only 180 degrees in a triangle. So x has to be 60, we know that. All right, we're going to move on to another angle, and we can do that using the law of sines now because we do know that 7 is a side and its opposite angle is 60. So we'd have sine 60 over 7 is equal to sine y over 8. Cross multiply, and you're going to get 8 sine 60 equals 7 sine y. Divide by 7. 8 sine 60 over 7 is sine y. Punch that into your calculator, take inverse sine, and you will get y is about 81.79. Y is, again, it's tricky. I'm not sure if it's obtuse or acute. It's very close. So I have to check the other possibility, and that would be 180 minus 81.79, which is 98.21. So y is just very close. I can't tell which one it is. It actually, it looks a little obtuse, but again, you're not sure. So just leave that and go on and figure out what z is. So we can use the law of sines again. Sine 60 over 7 is sine z over 5. And if we cross multiply and divide, we get sine z is equal to that. If we punch it into the calculator and take inverse sine, we're going to get that z is about 38.21, or since it's possible it could be obtuse, even though it's obvious it's not. I'm just putting in the other value, 180 minus 38.21 or 141.79. If you look at all three angles, X, Y, and Z, the only way to make it add up to 180 is to use these angles, 60, 38.21, and 81.79. So looking at that angle, you might assume it's obtuse, but actually in this situation, if these are really the side lengths, it has to be acute. It has to be 81.79. Okay, here's another one where it's pretty obvious that M is obtuse. I think we can pretty much assume that it's obtuse. Okay, so we don't have an angle on its opposite side. We can't use the law of sines, so we will use law of cosines. Since we have the angle 28, we will use the side k to be on the left side of the equation, and we'll put k squared. Therefore, we will put 28 into the cosine at the other end of the equation, and the other two sides, 10 and 14, will go in the other spaces in this equation. 10 squared plus 14 squared minus 2 times 10 times 14. And now we can just multiply that whole right side out and take the square root, and we get that. And then k turns out to be 6.98 about. All right, so we can now use law of sines to find the other angles. So sine 28 over 6.98, which we just found, is equal to sine b over 10. If we cross multiply and divide by 6.98, that is sine b. If we punch that into the calculator and take inverse sine, b comes out to be 42.26, or it could be 180 minus that. Clearly it is acute, but we'll see what happens. Sine 28 over 6.98 equals sine m over 14. If we cross multiply here and punch it into the calculator, take the inverse sine, we get that m is 70.33, or it could be 180 minus that, which is 109.67. Now, clearly it's obtuse. And also, if you look at the three angles we have to deal with here, we have 28, we have M and B. The only way we can get three angles to add up to 180 is if we use the obtuse M and the acute B. So those are the values that we have found for the unknown parts. Okay, the figure shows two cables that are attached to a vertical tower from a point on the ground. The angle between the cables is 15 degrees. The longer cable is 150 feet long and is attached to the top of the tower. The shorter cable is attached to a point 50 feet below the top of the tower. Find the length of the shorter cable. So we want to find the length of the shorter cable, and we'll call that X. And before we can find out what X is, we are going to have to find the angle opposite X up here. We can actually use the law of sines because we have 50 feet for that short side, and the angle opposite that is 15. So we can say sine 15 over 50 is equal to sine b over 150, because 150 is opposite b. So if we find angle b, we can cross multiply. So if we divide by 50, we are going to get 3 sine 15 is equal to sine b. And then if we punch that into the calculator and take the inverse sine, we're going to get that b is about 50.94, or 180 minus that, which is 129.06. So we can clearly see that b is obtuse, so we're going to choose 129.06. And now we can use that to find the other angle, because the angles in the triangle have to add up to 180. So 180 minus 129.06 minus 15 is going to give us that third angle to be 35.94 degrees. So we'll use that to find X. So sine 15 over 50 is equal to sine 35.94 over X. So if you cross multiply and divide by sine 15, you're going to get 113.38 feet for the shorter cable.